So, okay, so we were doing, so can you hear me?
Yes.
Yeah, okay. So we were doing Fourier analysis, okay. So we did some L1 theory. Of course, Fourier analysis is a vast subject, and one can give a full one semester course on that. So this is just I'm taking 2 classes on that. Okay, so it's very minimal, very basic. So now we will do the L2 theory. So before doing the L2 theory, we will recall what is the L2 theory for Fourier series, which we have already recalled in the last class. So in L2 theory, if we have a Fn, L2 of 0 to pi. The point is in Fourier series, when the measure is finite, L2 is contained in L1, of course. Okay, so maybe it will not be equal, but it's contained in that. So then you define f hat at n for n in any integer equal to integral 0 to 2 pi e power the f will be there. F of t e power int dt. So this is how we define that. There may be some constant somewhere. So this is how you define it. But this is nothing but in L2, this is nothing but when f is in L2, this is just f en, where en equal to en at t equal to e power int. Okay? This is just the inner product between them. So this implies f equal to summation n in z, n in integers, f hat n, which is the inner product. Then you take this ent f of t. Sorry, it's not f of t. It is just the f is equals in L2. Okay, in L2. As a L2 function, these two are equal. En. Okay. So as L2, this summation converges and converges in L2 and they are equal. In particular, this says that, I mean, then you can, if you have any L2 sequence, you can get a Fourier series by this. If you do this inverse Fourier transform, if you have anything, any numbers, an contained in small L2, then you can define, this is of course you have seen orthonormal basis. Because of orthonormal basis, you can define this function. Okay? This is equal to some f of t. This will give a this is in L2. So this way, this f going to f hat is a unitary between L2 of 0 to pi to L2 of z. Okay? So this is a unitary between them. So we want to prove a similar theorem for L2. Okay? But when the measure is, our measure is Lebesgue measure on real line, which is not a finite measure. So L2 is not contained in L1, and neither L1 is not contained in L2. It's there is no, they intersect. The intersection is dense, but then they are not. There is no connection between L1 and L2. Okay? In R, L1 R intersection L2 R. I mean, we have defined our Fourier transform. We define for f in L1 of R, we define f hat at xi equal to integral over R f of x e power minus I x xi dx. Okay, this is how we defined our Fourier transform. So we can define this. So this, I mean, when f is in L1, we can define it. F is in L2, we don't know whether we can define it. But we can define it, so we can restrict the Fourier transform, the Fourier transform to L1R intersection L2R. Okay. But then this is contained in L2R and this is dense there. Why is it dense? It's clear. I mean, both L1R, L2R contain simple functions, and simple functions are always dense in L1, L2, LP, and you know that it's all dense there. So because of that, we have that L1R intersection L2R is dense there. Okay. So now we can define for this intersection the Fourier transform. We want to say that, so which is a linear map. Fourier transform is a linear map. We want to say that See, we want to say that that extends to a unitary isomorphism between L2R to L2R. Okay, we want to, that is what is called Plancherel theorem. Okay, so maybe I will define script f of f equal to f hat. Okay, then script f is a unitary, extends to a unitary. Okay, this is for f in L1 or intersection L2R. Okay. Then script f extends. This is only defined on a dense subspace. Extends as a unitary map. Is a unitary operator between L2R to L2R. So it maps L2R to L2R. And it is unitary also. It preserves the norm, it preserves the infinite product. The point is in L1 there is no such theory. If you have a f in L1, then f hat we know that that is in C0R. It's continuous. Okay, and here such a thing need not be true. And another thing is there is no reason it is in L1, and it will not preserve the norm also for all L1. Okay, but this is true in L2 case. So which is the Hilbert space theory. It's true there. Okay, this is the theorem we want to prove now. Okay, so what do you want to prove? We want to prove that this Fourier transform, which is defined in L1R intersection L2R, extends to a nice unitary operator between them. Okay. So if you have any question, ask me, please. So then I will realize that someone is listening. Okay. So before that, I want to prove a lemma. Okay, these are all some general, I should have done it earlier, but I will just tell you now. If T is a linear map, see if you have a Banach space, even a Banach space is enough. If X naught contained in X is a Banach space, okay, it's a Banach space. Okay. This is a dense subspace. Okay. Then if you have a T defined from X naught to Y, from Y is another non-linear space, okay, some non-linear space. Okay. And if T is bounded on X naught, then there exists a T tilde from X to Y, X to maybe Y closure, whatever, Y completion, whatever, such that T tilde restricted to X naught equal to T and norm T tilde is equal to norm T. Linear. Okay. This I leave it as an exercise, which is clear, but it's I will tell you the proof orally. T is a uniformly continuous function. The basic analysis theory will tell you that if you have any function which is defined on a dense subset, and if it is uniformly continuous, if it is continuous, it's not true. 1 by x is an example. If it is uniformly continuous, then you can extend to a again uniformly continuous function to the closure. So that is what's happening here. You can extend to a uniformly continuous function. But in this case, it will be linear because limit is linear. And you can prove that the norm is also continuous because norm is continuous. All this, I mean, the initial Banach space norm is continuous. Using all that, you can prove that norm is also preserved. It's very easy to prove this. Okay. But this is just a lemma which I am supposed to have told you earlier, but I'm telling you now. But this is, I don't want this. I want to prove the following lemma. The following lemma is the following. So let HK be, well, inner product space is enough. But let me use Hilbert spaces. Then S contained in H be a total subset. I will tell you what total is, meaning that is span. This is the definition of totalness. Okay, we say something as generating, but here it's span S closure equal to H. Okay, any such subset we call it as a total subset. Okay, so we have a S contained in H, which is a total subset, and U is a map from S to K, satisfying ux uy equal to xy for all xy in S. Okay. Then there exists a, we may call it u itself. I mean, when we work with that, we call it u itself, but let me say it's a u tilde from, what is it, from h into k itself, because it's Hilbert space. I don't take the completion anymore. H to k. Then there exists a isometry. I want to say there exists a, I mean, it preserves inner product. It will continue to preserve inner product. That's what we want to say. Then there exists isometry, okay, u tilde from h to k, such that u tilde restricted to s equal to u. Okay. So if we have any total subset in which, if suppose something preserves inner product, then it extends to an isometry. This is not true for norm. If it preserves norm, there is no reason. Okay, because norm is not linear. Okay. So yeah.
Is there any difference between shorter basis and total subset?
No, this is not linearly independent or something. This is just a total set. There is no, that's not a basis. Linearly independent set is a basis. I mean, it's a total set, of course. You take the span closure, that's also. I'm just saying this is just a total set is enough. See, the point is, it's not just that. It's also, there is a well-defined. The point is, if it preserves the inner product, you don't even need to see when you. The point is, when we work with, when we want to define new objects, new operator or something, we can define it on a low total subset. And then suppose if it preserves the inner product, there is no need for us to verify the well-definedness even. I mean, there will be some sort of see, how will you extend this? You will take the linear combination of S, and then you define linearly on that. Okay, and then you have to show that it is uniformly continuous on that, so it extends or something. But then you don't need to even verify the well-definedness in this. Even well-definedness will also be true. Okay, there exists a well-defined unitary, well-defined unique well-defined unique isometry, such that u tilde restricted to this is yes. Further, I want to say two things. Further, u tilde is unitary if either one of the condition is satisfied. Of course, we know the following is immediate because we have discussed unitary isometry, and I am just going to state one of the condition is satisfied. First one is u tilde of S, u of S, sorry. We are working with that u of S contained in K is total. Okay, that is one thing. Or there exists a u star. I mean, and u tilde is extended, so u tilde star is also an isometry. Okay, we will use the second condition. This is clear. Okay, something, an isometry is unitary if and only if star is also an isometry. Okay, that we have proved. Okay, because of that, this is true. So the second part is easy. Second part is immediate, which we have already done. The first part, I leave it as an exercise. I will tell you how to do it. The exercise is you take linear combination. Okay, so you define linear combination. You define it to be extend it linearly. Of course, when you define it on S, and the span of S, you can define it by linearity. Then you verify the inner product between summation lambda I xi, summation lambda I yi, something, summation mu I yi. Then you take the inner product. Because inner product is linear, you can take the lambda I and mu I bar outside, as mu I bar outside. Then that will preserve the inner product. So it will become the u will go away. Then you take the scalars inside again. Okay. So that's why it will preserve the inner product on the linear span also. Once it preserves the inner product, it preserves the norm also, of course. So since it preserves the norm, it's well defined. You don't need to check that it's well defined, because for different linear combination, it's same because it's well defined. If you have two linear combination, then the difference will be 0, and you can check that it's actually well defined. You don't need, see, if S is a basis, f is s is linearly independent, then it is automatically well defined. But you don't need that. Even if it is just a total set, because of this, because it preserves the inner product, it will be automatically well defined. Okay, so that also you get convinced yourself. Okay, it is well defined. And further, because it's already, I mean, because it preserves the inner product on a dense subspace now. Okay, it extends because of uniformly continuous. Okay, and its norm is 1 and it's unitary. It's further continue to because of due to continuity, thanks to continuity, it will continue to preserve the inner product. So it's an unit. So it's an isometry. And the second condition is obvious. If it is that is also total, then u tilde will be on to. If that is total, u tilde will be on to. And otherwise u star. So you verify these two first condition. Second one is clear. Okay. So this I leave it as an exercise for you to go through. Okay, it's not difficult. But if you have doubt, you can ask me now. If you have any doubt on this. Okay.
Sir,
Otherwise,
please show the first lemma.
first lemma. First lemma. First
Yeah,
lemma
this one.
says that in any bounded linear operator can be extended. That's what the first lemma says. Okay. Second lemma says anything which preserves the norm or inner product. If it, I mean, if some isometry preserves norm, that is enough. It preserves the inner product also by polarization identity. Okay. So suppose if it preserves the inner product on a dense subspace, it will continue. You can extend it to the whole space, and it will continue to preserve the inner product. That's what it says. Fine. First lemma is fine. First lemma just says that any bounded linear operator can be extended to its closure, and the range will also get to the completion. That's all. If the range is Banach, you don't need to complete.
And so do we like what? Do we automatically have some sort of uniqueness about T tilde?
It is
The
of
first
course
lemma.
unique. Direct is uniqueness. It is unique. Yes, both the places it is uniqueness. I mean, when uniformly continuous function you extend to the closure, the extension is uniform, of course. It's well defined and uniform. You see, sorry, uniqueness, unique. Sorry, it's unique. Right. Fine. So it is this lemma I want to use. How do I want to use? We want to prove the Plancherel theorem. What is Plancherel theorem? We have defined our Fourier transform on a dense subspace of L2, okay, which is L1R intersection L2R. I'm just going to take the step function, the simple functions. Okay, I'm just going to take the simple functions. Not even that. I'm just going to take the characteristic function or indicator function, which is a total subset. Okay, I'm going to check it preserves the inner product. Okay, so it will extend to an isometry. Then we'll consider the. Then will I prove I will define the inverse Fourier transform and prove that that's an adjoint, and prove that the adjoint is also an isometry. That also preserves the inner product in a total subset. So that's also an isometry. That finishes the proof. Okay, so I will write one by one. Proof of Plancherel theorem. One second, I will just charge my computer. And for some reason, my iPad didn't get charged. I don't know why. First, I will charge the computer. If this goes away, then I will charge that also. Okay. So, proof of Plancherel theorem. Okay. So, define, maybe call it scriptive. I don't want to call it scriptive because I'm going to multiply by a constant later to prove it unitary, because I will get a constant times unitary. Because as I told you, Fourier transform, I define it up to a constant. So I will find a constant and using that I will define. So for the time being, I define f, but I will change the definition of f if it is okay with you. Okay. Define f of f. F is a, because f is in L1 or intersection, it's a slow battery. 10% is there. L1 or intersection L2R. I don't know how I would write from there. Maybe I'll remove my video and then go there. Okay. So we define. So first, I want to verify that. We want to verify the following. One, script of 1 AB, some interval. Okay, script of 1 CD, another interval. This one, you know, this is the indicator function. Okay, the characteristic function of the interval AB equal to 1 AB once, the inner product once. Okay, but then since indicator function 1 AB, with indicator with AB finite, okay, A less than B less than infinity greater than minus infinity. This set is total in L2 of R. Okay, script F will extend. If I prove that, if I prove this, if I prove star, will extend to an isometry on L2 of R. Okay, then I will define the Fourier transform, the inverse Fourier transform, script of star, okay, on L2R again by script F star, I mean on L1, L2R intersection L1. Okay. F star of F equal to integral over R, F of
Sir, what is that statement?
which statement?
If star is proved is total in L2R, is that the statement?
No. If it is like this, sir.
Oh,
Okay. That is total in L2R. Then if star is proved, then F will extend to an isometry on that. Okay. Then we define F star on L1R intersection L2R by F e power Ix t, okay, F of x dx. Whatever. It is just the inverse Fourier transform. Instead of e power ixt minus ixt, I use e power ixt. That's all. That is the inverse Fourier transform. Sometimes that is called as this is called like this. I mean, Fourier transform is defined like this. No, Fourier transform is denoted like this, but this inverse Fourier transform is denoted like this somewhere. Because we use the ixt. Okay, so that is what I use. This is equal to, maybe I write it here. F inverse hat. Okay, so that is defined by e power ixt. Okay, so then I define f star and show. I mean, this is what I'm going to do. Okay, that's what I'm saying. So f g equal to f script f star. Okay, I will show this. I mean, f star is just a notation there. Here I am proving that it's actually an adjoint. So I first prove, I define the Fourier transform in the intersection. Then I prove that it is actually, it preserves the inner product of the total subset, which is the set of all indicator function or characteristic function. So that will make sure I get an isometry on L2 of R. Then I prove the inverse Fourier transform and show that it is actually an adjoint of this. And since we have already, I mean, the inverse Fourier transform is almost same as that. This F, notice that F hat of t is nothing but F hat of minus t, right? So it will also preserve the inner product. You don't have to verify that again. This is also an isometry. So we will prove that that's also an isometry by the same, if you want by the same prescription, same way. That's also an isometry. Because of that, since we have an isometry which is an adjoint, the Fourier transform is a unitary. That's what we want to prove. Okay.
Sir,
Yeah.
so like what have you written in this line? So like we define f star on L2R intersection L1R by f star of what?
F star of f at t. F star of f is, it's again a function at t equal to integral f of x e power ixt dx. Yeah, that's right. You take it e power ixt, you multiply by e power ixt and then integrate on R. It's similar to Fourier transform except up to a minus sign. That's all. Right? That's what I said. F hat at t is nothing but f in. I mean, the inverse Fourier transform at t is the Fourier transform at minus t. It's not precisely that. There will be some constant playing around. That's all. It's fine. Is there a
Yeah.
problem? Did I write anything wrong? What's
No,
the
like it's fine. It's fine.
It's fine. Okay. So I'm just saying that we will define an isometry. We will prove, we will define some Fourier transform on the total subset and prove that it preserves the inner product. Then we extend it as an isometry. Then we have the inverse Fourier transform, which is almost like Fourier transform. It's the same as Fourier transform up to a minus sign in T. Okay. Then that also preserves the inner product, and that we prove that that's an adjoint. That's all. It's an adjoint for all. I mean, this we will prove for all FG indicator function. Okay. FG inside. Yes. I call that as yes. Again, yes. That S equal to this. My S equal to all indicator function of intervals. Okay. Which is a total subset. On this, I want to preserve. So, first statement script FF to prove script FG equal to inner product FG for all F and G in S. Okay, that's what we want to prove. Okay. So we must verify, we will do it in several steps. It's easy, but still we will do it in several steps.
What is S7?
S is the all indicator functions of the interval.
Oh, yes.
Okay. Okay. So now let F equal to some 1 AB. Okay. Let us verify that the Fourier transform preserves the norm up to a constant. Okay, sorry. This is up to a constant, okay? I mean, this is, I will say that it's a constant, then I will divide it by that constant, okay? Equal to C times F of G. Please bear with me. I'm abusing the notation. I'm rigorous, but I'm just abusing the notation. I have defined Fourier transform, which I want to define up to a constant. So this inner product will be up to a constant. Then if I put a root 1 over root C, it will preserve the inner product. Okay. So for some C, and of course the C is uniform. It does not depend on F and G. Okay. Let F equal to 1 AB. Then we calculate what is norm F2. We want to norm F2. We are working in a L2, so we have to find norm F2. So norm F2 equal to integral A to B. It's just 1 dt, which is just equal to B minus C. It's just the number B minus C. I will mute my video and then go somewhere else and connect there. Okay. So norm F2 equal to B minus A. Okay. We want to prove that the Fourier transform also has the same norm. Okay. So what is norm F hat for this? So first let us calculate what is.
So won't there be a square root?
No, there is no square root. You have F square, which is also 1. Oh, you want to, yeah, there is now F2 square. Good, correct. Yeah, there is a square root.
Okay.
Right. Okay, norm F2 square equal to B, which is correct. Okay. Now let us calculate norm. Let us find what is F hat. Okay. F hat at let me say T instead of xi, I make it confused. F hat at T equal to integral of over R of F of e power minus I x t minus tx, sorry, minus tx dx, which is equal to integral over A to B. So that is 1. So itx dx, which is equal to minus ix, right? No, minus it. Minus it e power minus I b t minus e power minus I b t, right? So this is our Fourier transform, which is a nice continuous function. Of course, that is always the case because it's in L1 already. Okay. So this is f hat t. Now we want to find what is f hat t norm square. Okay. Which is equal to integral over r. Integral over r. So e power I b t minus e power I a t by I t minus I t into bar of that e power minus I b t e power minus I a t by minus I t. Okay, there is a bar. So you can bring the bar to the both numerator and denominator. This will become I. So I times I is minus 1. There is a minus sign, so it will go away. You will get a t square in the numerator. Right? Okay. Hey, I see that my iPad is not charging for some reason. It's still showing the same percentage. If it goes away, then I don't know. I will stop and then continue tomorrow. I don't know. It's not charging actually. Suddenly, I noticed that it's not charging. I don't know why. It's still showing the same amount of, same percentage of battery. Of course, if it charges, then I will continue. So if you multiply those two things, I'm going to get, I mean, these two things will give 1, that's 1. So this is 2. Minus then the real part of both these things. E power IAT minus e power IBT. So it will be, there will be a 2 times real part of that, which is 2 times power cos B minus AT, right? B minus A xt, no? B minus A, no, B minus AT, correct. Times T over R, correct? Which is equal to 2 into 2, which is 4. 4 integral over R. And what do we get? Integral over R. 1 minus cos B minus A is sine square B minus A t by 2, okay, divided by t square. Correct. Okay. Now let u equal to, substitute u equal to B minus A t divided by 2. So this implies this is equal to 4 times integral over R sine square u. So t square is u square times, so you have B minus A square, 4 on the top. Okay. Then into du equal to B minus A by 2. B minus A. The whole thing will give us, possibly there is a 8 or whatever, some constant, it doesn't matter. But the point is, I will get a B minus A. Will I? Yeah, is this okay? B minus A into integral over R.
Shouldn't that b minus a be in the denominator?
B minus A should be in the denominator.
Yeah, like I think the constant should be
No,
8 by
I
b
wrote
minus.
it wrongly. No, it's B minus. No, is there anything wrong in what I have written? Why is it in the denominator?
Like there's a b minus a whole square in the denominator.
Right. So,
So like the
oh no, I have to substitute for t. So t equal to u by b minus a square. So it should be in the top. Sorry. No, u equal to b minus a by t. So I have to substitute for t. So t equal to 2u by b minus a. Okay, which is, so it's 4 down. Okay, and b minus a square on the top. Okay. Then du equal to, so then I have to substitute for dt, which is du by b minus a. Okay, it's correct. So the whole thing will give me this, I will get a 2 here. Let me write it again. Please tell me if it is correct. Before that, I have to write something. B minus A into 2 integral over R sin square U by U square is okay. I call this as C, which is equal to C times B, which is C times norm. So this is integrable. Notice that sin square U by U square is integrable. I mean sin square, I mean this is just sin x by x, which is a continuous function in the interval -1 to 1. I mean it has a problem at 0, but then you can define it to be 1 at 0. It's a removable discontinuity. Okay, you can define it to be 1 at 0. Then it becomes a continuous function on a compact set, so it is bounded. And then 1 by U square is integrable. Okay, outside the interval -1, 1 by U square is integrable. So this is an integrable function. So this is norm f2 square. Okay, so this is okay. So we have proved that for f equal to 1, for f in the form, for all f in S. This is fine. Okay, but we have to verify something else. We have to verify that it preserves the inner product. Okay, now suppose now let f equal to 1 AB. Is this okay, the verification? And G equal to 1 BC. Okay, I'm just starting with B. Okay, BC. Then norm of, let me write it like this: G hat plus F hat norm 2 square equal to norm F hat square plus norm G hat square 2 norm plus 2 times real part of F and G, right? But then F hat F plus G, this is the, I mean, this is equal to F plus G hat. The Fourier transform is linear, okay, F plus G hat. But then F plus G equal to 1. I'm just starting the G with B, no? So 1AB plus 1BC is 1AC, right? Because it's indicator function, which is just 1AC. So norm of F hat plus G hat square equal to C minus C. On the other hand, this is norm F hat squared equal to B minus A, and that is equal to C minus B, okay, plus 2 times 2 of F real of G, which is equal to C minus A plus 2 times real part of Fg. I mean F hat G hat, right? So these things implies 2 times real part of F hat G hat equals 0. Okay. For F in this form, F is in AB and G is in 1 BC. Okay, this is just all silly verification, but we have to do it. Now, suppose F equal to 1 AB, okay, and I mean, so what we have proved is if F is of the form some 1 AB and G is of the form 1 BC, it starts with B, then the Fourier transform, it preserves the inner product for this kind of function. That's what we have verified. Okay. Now suppose we take some other G equal to 1 CD. Okay. Then we can write FG hat, okay, equal to, we take, I mean, let me write directly the function 1. Let me not write this. Let me directly write the indicator function here. 1 AB plus 1 BC, okay, indicator function 1 CD. Okay, now we know that this is equal to 1 AC, 1 CD. But we have noticed that if it ends with C, it is equal to 0. But then this is equal to 1 AB, 1 CD. Maybe I put a hat, sorry, I put a hat. Okay. Plus 1 BC hat, 1 CD. Now we know this is equal to 0. Okay. So we know, so these things imply that 1 hat AB plus 1 hat CD hat equals 0. That is, sorry, we have proved only the real part is 0. I'm sorry, this is just the real part. Real. We have only proved real part. Real part, everywhere real part. So we have proved that the real part of FG, okay, let's one second. Let's just wait. On the other hand, if, I mean, there is no relevance for the real part. The inner product will be real. So if F is in, you know that if these are all real valued function. I'm just saying the inner product between the Fourier transform is also real. If F, G are in yes, okay, then F hat of T, it's a real valued function. F hat of T bar equal to F of minus T, right? This is equal to integral F of X e power I X T, okay, the whole bar. That is equal to integral of F of X e power. You will get the bar here, which becomes IXT, which is equal to F hat at minus T, right? That's what I'm saying. So this implies the inner product between F and G, F hat G hat, equal to inner product of, I mean, you take the bar, for example, then it's the bar of F hat of, this is going to be F hat of T, G hat of T bar, dt. That's the inner product, okay? Then the bar goes inside and this becomes F hat of minus T, G hat of minus T, the bar goes inside, so it becomes like this. But then when you integrate with R, you can change T to minus T, it does not change the integration. So this is also same as F hat G hat. Because of this property, I mean, the F and G are real value. I mean, it just takes the real value. It takes the value 0 and 1. On the other hand, F hat and G hat satisfied. F hat at T, F hat, the bar of F hat is F hat at minus T. But then the integration, it does not matter whether you have minus T or T. You can change the variable to T to minus T. You will not, there is nothing will be changed. Okay. So these things implies that you can forget the real part. These things implies that F hat, what does it mean? These things imply that real part of F hat G hat equal to real inner product of F hat G hat for all Fg in S. In particular, we have proved the real part of any two disjoint. I forgot to say this thing should be in disjoint interval. A less than B less than C less than D. Okay. A, B and C, D are disjoint. Or it can be, I mean, A, B and C, D are disjoint. That's what I want to do. Okay, maybe with A, B intersection C, D is empty. If you take indicator functions of two disjoint interval, then we have proved that the real part of the Fourier transform of those functions is 0. But then there is no relevance for real part, so it's the same as. We have proved that, I mean, this is what we have proved. Indicator function of 1 hat AB with 1 hat AB, okay, equals, which is just the norm of that, which is same as 1. I'm just saying, if you just convince yourself that I'm just saying that integral F hat G hat, this inner product is same as Fg for all FGs. We have proved that if it is the same function, then the inner product between the same function f and f hat and f hat is just the norm of that. That is preserved. We have proved that first. Then if it is disjoint interval, then the indicator, you take the indicator function of that. The inner product between the Fourier transform of the corresponding Fourier transform, inner product of the corresponding Fourier transform is 0. Of course, the inner product between two indicator function of two disjoint interval is also 0. So the inner product is preserved for disjoint function. Then you can write any 1AB, 1CD as something what wherever it intersects. Okay, 1AB intersection CD. Okay, 1AB. I mean, you can write it as the intersection. You can write the CD as the intersection of AB and then the whatever the left in the disjoint one, which may be 2 intervals. Okay, so you verify that the inner product is preserved. Very easy to verify. Is this clear? I will not go through the simple verification. Is this fine? I don't see any answer. Hello.
Yes, sir. Yes.
It's fine. Okay,
Yeah.
fine with everyone. Anyway, you convince yourself. There is really no great trick. Okay, it is just linearity of the inner product. And if you have any indicator function, okay, you can, if you have any indicator function, A union B, A disjoint union B is 1A plus 1B. Okay, that is what I am using, nothing else. Okay. So I don't want to write each and every detail. Okay. So we have verified that the Fourier transform preserves the inner product on the, I'm sorry, I forgot there is a C here. There is a C. So we have proved script f script of G equal to C times Fg. So we have proved that script f extends to L2 of R and this is equal to C times Fg. Okay. Okay. Now we have defined f star. Now f star, which is defined f star of f at t equal to integral over R f of x x e power itx dx. Okay, this is the same thing. Now f star of f star of g is also equal to c times fg. Okay, for all fg in, for all fg in L2. Now f star also extends. Same way, f star also extends to L2 of R, and that also preserves the inner product. Okay. Now we are left to, so f star is also in isometry. F is in isometry, f star is also in isometry. We just want to verify they are adjoint to each other. Okay. We only need to prove there is a C, so we only want to, so in particular norm, okay, I write 1 by root C of Fg square equal to 1 by root C of f star of G square equal to norm G2 square. Okay, this is okay. So if you take Fg square, you will get a C there, and that C will be divided by this. Now we want to verify. Okay, this we have proved. Sorry. We only need to verify script of G, maybe script of F G equal to F script F star G. They are adjoint to each other. And we have isometry, which is two isometries which is adjoint to each other, means they are both unitary. That's what it says. Okay. So it is enough to, again, it is enough to verify for Fg in S. Since, why is it true? Since inner product is linear and continuous. We have already proved that both of them extend to isometry. Okay, if it satisfies this inner product relation and a total subset, then it will satisfy on the span because inner product is linear. Then it will satisfy on the whole of them because inner product is continuous. Okay, so we only have to verify it for simple indicator function. I mean, we can verify for simple function by linearity. We want to verify for indicator function. Okay, so now let f equal to 1 AB, okay, g equal to 1 CD. Okay. Then integral, inner products of this g equal to inner product over R. Maybe I will directly write it. I hope you will be find it okay. This is the inner product. We want to take the inner product with G, so that will become CD. And inside it will be this script of this Fourier transform. I'm writing it here, which is just AB e power minus IT I Tx, Tx. Okay, this is a function of T. And then I am integrating with respect to G. So this is just dt. Is this okay? Script f. This is script f. Okay. And G is indicator function between C to D. So I have written the integral between C to D. This is fine. Do you want my video?
Yeah, this is fine.
Maybe. How do I do? This is okay. This is okay. Okay. I'm in a clumsy position. So this is fine. So this is our whatever. This is our inner product, whatever the inner product we have. Now we interchange this is just a nice function, continuous function, and we are just integrating in finite interval. So this is same as integral AB. We take the CD inside, okay, integral CD inside. And then I change it to e power itx, okay, e power itx dt inside with respect to CT. Then I put a bar here, dx. This is okay. It's the same thing, right? It's the same thing. I'm just rewriting it like this. But then this is exactly equal to this. Okay. So we have verified it's an example. Theorem is proved. Up to a constant, I have defined the script f to be something, but you have to divide it by 1 by root 2c. Up to that, maybe I'll write 1 by root 2c from L to R. L to R is unitary with 1 by root c. Script f star as inverse. Okay. I don't know. It is not. It's still showing 8%. It hasn't come down. I don't know why it's not charging. It is still showing 8%. Maybe it will charge. At least it's not depleting. Okay, so this is fine. Any doubt? Shall I move on?
Yes.
Okay. So the Fourier analysis is over. This is what I want to prove. This is what is called Plancherel theorem, and I have proved Plancherel theorem. Now, if you don't mind, I will take another half an hour to prove open mapping theorem, or I will do it with the presentation tomorrow or something. In this course, I am left with only one thing, open mapping theorem, and some examples how open mapping theorem can be applied. Okay, then there is many things in the presentation. I will say something during the presentation, during closed graph theorem, uniform boundary school. I will say something. Okay, I will make some.
Sir, I have to present that topic. So in your email, you said that I'm supposed to present that tomorrow. Is that the case? So closed graph theorem.
I have replied you. You didn't get the reply? I replied.
No, I got that. I didn't get your latest reply after that.
It is on Thursday only. By mistake, okay. I wanted to write Thursday, but I wrote it tomorrow, as I usually do.
Okay.
Yeah. So it's my mistake, misrepresentation.
Okay.
That's all. So before that, so on that day I can prove, on Thursday I can prove open mapping theorem. Then Lakshay can continue, and somebody can continue after that. Is that all right, or shall I prove open mapping theorem now? You can tell me if you have anything else to do. It will take some time. Shall I continue now? So since I don't find anything, I will start open mapping theorem now. Is this okay? If you have any objection, you tell me now. Otherwise, I will it will not end in 6:15. It will take some time. But I will end the course with this. Okay, we will have only presentation after this.
Sir, will the contents of the presentation will all be in the exam?
Yeah. See, the point is, I will set the exam paper for some 300 marks. Okay, surely. So you shouldn't have any complaint. More topics means it's more choice for you. That's all. Okay? If you have any complaint, you just study 1/3 of it and you just solve 1/3 of the problem. You will get 100 even after that. Okay. So I will not include measure theory in the exam syllabus. Exam is after beginning. Whatever we have done after midterm. So it's only the syllabus is after midterm. Till what we have done till now. Everything included. Okay.
Sir, LP spaces and Holder, Minkowski, those things there.
Holder Minkowski has already done. But LP space as a Banach space, I don't plan to ask any question. Let me see. Even if it is there, it will be above 3. It will be much more than 300. Okay, more than 300. I will set the question paper for more than 300. Okay, if you have done reasonably 1/3 of it thoroughly, you should be able to score 100 marks. That's all. Okay, so you shouldn't complain anything. Even if there is a question which is wrong or something, so it's not high school. You shouldn't complain that the question is wrong, so I should give mark. You shouldn't complain. You should find that it's wrong, and you should come to a conclusion. You to come to a contradiction or something. Okay, so I will set it. You can leave the question and do something else if you have some doubt on that. Okay, but there will be a lot of choice. I'm sure there will be very reasonable question up to 200 marks. So you have to solve only half of that to get 100 marks. To get even 100. Okay. Is this fine? So
Yeah.
what I have written, open mapping theorem. No, it's something else. Showing something else. Okay, shall I continue this? Open mapping theorem?
Yes, sir.
Okay, I will continue with this. So the open mapping theorem is the following. Okay, it says the following. If you have XY or two Banach spaces, now we are working with Banach spaces. Okay, this is an application of bare category theorem. Okay, that's why we need bare category theorem, which is already. XY are Banach spaces, and it's important that they are Banach space. Please remember that it's a complete space, it's a Banach space. Suppose if we have a T, a linear operator from X to Y, okay, surjective linear map, onto. Okay? It's an onto surjective linear map. Okay? So by bounded linear, what does it mean? It's continuous. Bounded linear means it's continuous. But then there is no reason it is an open map. By continuous means what? The inverse image of any open set. If you take any open set in Y, the inverse image of the open set is open in X. That's what continuity means. But the point is, if it is a linear map and if it is surjective, that is, it's onto a Banach space, you can actually remove this Y with a Y naught, which is a closed subspace of Y. Even that works. That doesn't matter. You don't need onto. Okay. If the range is complete, then the map is open. Okay? If it is surjective, then T is open. T is an open map. It's
Wait.
continuous. Huh?
You said that it has to be. We can always restrict to the range. We can only do that if the range is closed, right?
That's what I said. Range is complete.
Oh, okay.
Closed. Yeah. Range is
Okay.
a closed subspace of a complete Banach space. Of a Banach space. Right.
Okay.
That's what I said. Otherwise, we cannot do. The range of T sometime may not be closed. The range need not be closed always. So if the linear operator is such that the range is closed, then it is an open map. That's what this says. If XY is Banach spaces, this is the open mapping theorem. The statement is if XY is Banach spaces, T is a linear map, T is onto X to Y, it's onto bounded linear, then T is an open map. I'm assuming X and Y to be Banach space. You can replace Y by you can replace by the condition, surjectivity by the condition that T of X is closed. Okay.
Yeah.
Open in the range, right, sir? In case a range is not
Right. T of any open set is open. Is open. Sorry, is open.
Open in the range.
Of course. T of
Okay.
T maps in Y, no? So it's open. Subjectivity, you can replace subjectivity by condition T of X is closed. Okay. It's the same thing. Okay. Then you can work with that. Then it is on to under. So this is what we want.
Then the statement would be that T of an open set is open in T of X, right?
Correct. Yeah. Okay. So what do you want to prove? We want to prove that T of any open set is open. So, but then any open set is union of open intervals or open balls. So it's enough to prove any T of any open ball is T of any open ball. That is T of. I use the letter X or Y. Maybe I will write that. B of X bar Y or X, either X or Y. Okay, of R at X naught equal to all those Y in X or Y. I mean, this is not X quotient at Y, X or Y. Okay, you take X or Y such that Y minus X naught is less than R. It's just the open or ball around X naught with radius R that we call. So enough to prove T of any B or X naught is open in Y. But that is equal to T of any open ball can be written as like this: B of 0 R times B 0 1. Open ball, 1 is here. 1 at 0. Okay, is open. But this is equal to T of X naught plus R times T of B1 of 0. This is the open ball, the unit ball. Okay, the open ball around 0 of norm 1, of radius 1. Okay? So since addition, multiplication by R, multiplication by scalar, addition, they are all for R greater than 0. They are all continuous function with an inverse. Of course, they are all invertible and continuous, all these things. Because of that, we have that it's enough to prove T of B1. I call it as B1. B1 0 as called B1 is open. Okay, it's enough to prove this. Now the claim is the following. The claim is there exists a R greater than 0. I want to prove that this is open. For that, I have to prove that every point has an open ball around that which is contained in it. That's what the definition of open means. I want to prove that there exists a R such that by R. This is the open ball. I mean, I don't when I don't write the center, it is center is 0. Okay, by R equal to, if you want by R 0. Okay? This is equal to. So by R, there exists a by R such that by R is contained in T of B1 0. B1 T of B1. Okay, B1. This is X. I take the unit ball in X, and the image of the unit ball contains some open ball. It is enough to prove that. I am claiming this. Reason, the proof of claim. So why is this true? So for suppose Y is in T of B. Suppose the claim is true. Okay, I mean I'm saying it is enough to prove this. Enough to prove claim is enough to prove. Sorry. The claim is enough to prove there exists a R such that this happens. So if the claim is proved, then the theorem is proved. That's what I'm saying. So if we assume the claim, we want to prove the theorem. So we want to prove that T of Bx1 is open. Okay, we take a y in T of Bx1, then we want to find an open ball around that which satisfies. Now T of y r, B of y, B r of y. So the r is there, so I take something else here. I take r epsilon y, which is equal to y is there, so y and y is equal to tx for x in bx1, right? Y is in that means y equal to that, like this. This is equal to y looks like this is equal to b of y in r. So that looks like y plus b of the ball around 0 y epsilon. Ball around r epsilon. Now if b yr is contained in T of bx1, then by r epsilon is contained in b of b of x epsilon, right? Right.
Yes.
So because of that, this will look like this is contained in this is tx plus b of t of b of x. Okay. Now choose epsilon greater than 0, of course, less than 1 minus norm x. That is norm x plus epsilon is strictly less than 1. Okay. Now because of that, b of r epsilon y is contained in norm x plus epsilon. This is less than or equal to 1. So epsilon, because of that, this will be less than t of b x1, right? Right? This is tx. Norm x is, is okay. T of x plus something in bx epsilon. Okay. So whatever in bx epsilon has norm less than epsilon, x has norm x, of course. Norm x plus norm epsilon is less than 1. So the whole thing will be T of bx1. Okay. So this is what we want to prove. I'm saying that if we prove this claim, then we prove that T of b1 is open. If we assume this claim, then for any y, I have found an open ball around that, which is the ball of radius r epsilon, such that b r epsilon y is contained in b of x1. This is fine?
Yes.
Okay. Okay. So all we have to prove is, so all we are left to prove is we want to prove there exists a r greater than 0 such that by r is contained in byr is contained in T of bx1. Okay. Okay, this is what we want to prove. So now we want to apply the bare category theorem. How do we apply the bare category theorem? So we have y. So since T is surjective, okay, y equal to union of n greater than 1, maybe. It is just the increasing union, so it doesn't matter. T of bx, right? Okay. So by bare category theorem, there exists a n such that T of bx xn closure has an interior. Okay, so Y is a complete metric space, and we are writing it as a union of some countable union. So it cannot be written as countable union of nowhere dense subset. So at least one of the set has to be nowhere dense. Sorry, one of the set is not nowhere dense. That is, its closure has an interior. That's what it means by it. It's not nowhere dense. Okay. Okay. So it has a non-empty interior. There exists a n such that T of bxn has a non-empty interior. Okay. But then we want to prove that. So this implies, of course, we can divide it by n. I mean, we can. This has a non-empty interior. So this implies what? This implies you can divide it by some n, and that implies no. The point is this has a non-empty interior. That will imply that T of bx1. This has, I mean, you can divide it. This is a linear map, so you can divide it by that. That has non-empty interior. Okay, T of bx1 has non-empty interior. Okay. Now we want to say that. So suppose. So this is non-empty interior means we have something like this: y plus b of some y s around. I mean, that is how a open ball will look like. Open ball with center y and some radius s will look like this. This bys is a center with open ball with center 0 and radius s. Okay, so then this is contained in T of bx1 closure. But then this implies bys is contained in T of bx2 closure. Okay, both has norm less than. I mean, both they don't have norm less than 1. They are T of something of norm less than 1. By triangle inequality, they will satisfy this. So this implies b of y s by 2 is T of b x by 2 x 1. Okay, that's what we want. Okay, is fine. Is this fine? So we have proved that there exists here. We have proved that there exists here. So we have proved the following. Let me just conclude what you have proved. We have proved that there exists here. Maybe I call it. There exists t greater than 0 such that b of y, this t is that s by 2 is contained in T of b x1 quotient. But we want to prove that this byt is actually, there exists a byr in T of without the closure. That's what we want to prove. Okay, let us write what this means. This by2 is contained in this closure. What does it mean? It is contained in the closure means, suppose we have a y. So this means given, this implies given epsilon and delta greater than 0, okay, for y in byt. Okay, if we have a y in byt, no, I want to write something else. From this, I want to conclude the following. This further implies that phi y epsilon t is contained in T of bx epsilon quotient, right? For all epsilon. Because T is linear, multiplication is continuous, all those things. Okay, blah, blah. Okay, this is it. So this means the following. This implies for all epsilon delta greater than 0. And for y in this open ball, by epsilon t, that is norm y is less than epsilon t. Okay, that's what it means by it is there. Okay, there exists a x in x and norm x is less than epsilon, and this y minus the tx, okay, is less than delta. See, what we have is, suppose we have a y here, then there exists a x here such that tx and y are very close. That's what it means by it is in the closure, right? Okay, tx and y are very close. as close as you want. So that is delta close. So you choose a delta. Then if you have a y here, you can find a tx here such that the difference between y and tx is less than delta. Okay, the epsilon is in the open bar. So I am just translating the statement. Whatever the statement here, whatever the statement I have circled out, this statement, that means this. This is fine. This is fine. I'm just writing the definition of closure. Okay. Is this fine? I don't see anyone saying yes. This is. I hope this is okay. This is just the definition of the closure. Okay.
Yeah.
Right. You have that by epsilon t is contained in t of bx epsilon closure. That means if we have a y here, then there exists a x here, such that t of that x is as close as you want. That's what it says. Okay, and that close is given by that delta. So that's what I have written. Okay, so that's what I have written. Okay, now using this, I want to write some, get a sequence. Okay, this proof is I am just directly taken from Sundar's book. Okay, and you can find any book, it will be the same. Okay, okay. Now take epsilon equal to 1, okay, and epsilon equal to 1 and delta equal to half t. We will go on taking different epsilon and different t, different delta, and then we will get a sequence. And okay, and let y naught be in by t. Okay, by t. We want so. So this whatever this condition, we call it a star. Okay, then star implies for epsilon and delta. With this epsilon and with this delta, that means there exists a x naught in x naught with norm less than or equal to 1, norm less than 1, and there exists a x naught in the open ball. Sorry, x naught in the open ball, which I can write it as x naught in x with norm x naught less than 1. Okay, I'm just taking epsilon equal to 1. Okay, so I'm just writing the definition. Norm x less than epsilon, norm x less than 1, norm x naught less than 1. So, and y naught minus this tx naught is less than, so which is the delta. Delta I have taken it to be half. Okay. So in the next step, take epsilon equal to 1 by 2 and delta equal to 1 by 2 square t. Okay, then you will get let me just write, can go on like this. Okay, and take in the nth step, take epsilon equal to 1 by 2 power n and delta equal to t by 2 power n plus 1. Okay, and get sequence yn. You get a sequence yn in y and xn in x such that norm of yn is less than 1 by 2 power n times t, and norm of xn is less than 1 by 2 power n. Okay, and yn plus 1. You define yn plus 1 to be yn minus dx. See, in the next stage, I'm going to a smaller. Initially I have taken epsilon equal to 1. Then I am taking 1 by 2. Then I am going to take 1 by 2 cube. I go on like this. Okay, and I apply for the corresponding y1. See, initially y0 had norm 1. Then y1 has norm half, less than half. Okay, y2 has 1 by 2 square. So I can apply the condition star for y1, y2, go on inductively, I apply like this, I get a sequence like this. Okay. But then summation norm xn is convergent, is less than infinity. We have proved that absolute convergence implies convergence in a Banach space. So since X is a Banach space, notice that I'm using the fact that X is a Banach space. I have already used the fact that Y is a Banach space because I used completeness to use the Baire category theorems. I already used Y is a Banach space. Now I am proving X. I'm using X is also a Banach space. Since X is a Banach space, summation Xn is convergent. Okay? The limit exists for summation Xn. Okay. Okay. So now we have yn plus 1 equal to yn, which I have already written. Yx, didn't I write it? Yeah, yn minus txn. Yn minus txn. But then this is equal to yn equal to yn minus 1 minus txn minus 1 minus txn. So these things will go on like this, and you will get y naught minus t of summation up to n, k equal to 0 to n x, right? You take limit to infinity, but then yn goes to 0, right? Because norm yn is less than, you have that condition, yn goes to 0. Okay, so this implies, I'm not able to write it. So this implies y naught is equal to t of summation n equal to 1 to infinity x, which exists. That series, the limit of the series exists, but y naught equal to this. Correct? So in particular, this implies y naught equal to tx for some x. I mean, y naught is in the point is, I mean, we have started with the y naught, and we know that, so what is the norm of y naught? Norm of y naught is less than, sorry, norm of x is less than summation norm xn, which is less than, we started, initially the norm of xn is less than 1, right? So it should be less than 2. Right? We started with y naught is in b yt. There exists a x in b x2 such that tx equal to y. That's what we have to do. This this implies that b yt is contained in t of bx2. This implies b y t by 2 is contained in t of. That's what we want to do. Any question? Any question anywhere? Maybe I will go through the whole thing again. We wanted to prove that T of any open set is open. It's enough to prove T of any open ball is open. Then it is enough to prove T of the unit ball is open. To prove that, we used a claim that there exists one open ball around the center, around 0 with radius r is contained in that. That's enough to prove. We proved that is enough to prove that. Then we used the Baire category theorem to get a set with non-empty interior. With T of bx1 has non-empty interior. We proved, I mean, we want to get tbxn is non-empty interior. Then tbx1 has non-empty interior. Then we use this iterative method to prove that originally what we started with, that byt by t is contained in tbx2. I mean, we want to prove that it is T of some open set. That's what we want to prove. So once we have proved that, we take T r equal to T by 2. Tell me whether this is fine.
Sir, can you tell that? Can you tell the last step once more?
Last step, the whole thing. No, we proved something. We proved that. So let me. We proved that this B of y epsilon t. We proved that B of yt is contained in t. We proved that this whatever this t of the we proved that t of the unit ball closure contains interior. That means it contains some open ball. Okay.
Yeah.
So once we have proved, that means that you can divide, you can dilate it. This is called dilation. I mean, you can divide the t by epsilon or multiply by the t by epsilon, which is what is called dilation. You shrink it by amplification or dilation, whatever. So B of y epsilon t is contained in, we proved this. We have this. Then I wrote what it means in terms of, because it is contained in the closure, what it means. Then I continuously taken epsilon equal to 1 by 2n and delta equal to 1 by 2 power n plus 1 t. Can you mute it? It's echoing. I think my voice is echoing there. Can you just mute your video?
Oh, okay.
Yeah, please. Yeah. Now I have taken epsilon equal to 1 by 2 power n and delta equal to 1 by 2 power n plus 1 t and use the Banach space property of that so that some sequence is convergent to get to map this y naught as something as t of something. I mean, it will get mapped to something, but it's t of some nice ball. See, it has to happen for all this yt. You have b of yt. You have this b of yt. This is open ball of radius thing. The whole thing is contained in another open ball. Then you can dilate it to get it to another. I mean, the unit ball. And there, I mean, there, you may think that because there's subjectivity, there will always exist tx naught. That's not this. Y is arbitrary. This y naught is something arbitrary in byt. For that, I get some x naught in the open ball of radius 2, such that this y naught is the image of that x naught. Okay, for any y naught, I have a corresponding x naught in the open ball of radius 2. But then you can dilate it by again by half or something. Then you get for any y in the. I mean, then you get the b of. This is what we want to prove. Finally. Some b of. We want to prove that b of or y is contained in t of b of x. This is what we claim we want to prove, which is true. Okay. Is this convincing? You can go through the proof, the book, any book. Fine.
Oh, okay, sir. Yeah.
If so, we will meet tomorrow at 5. I am finished with the course. Actually, I have to say something about. See, the open map says the following. So this says the following. So anyway, Lakshay will say something about that. A corollary to this open map. So that is one thing. The open map says the following. If we have a t from x to y, suppose this t is 1, 1 and on 2. Okay, that means t is continuous. But then there is no reason it's a homeomorphism. Okay, the inverse need not be continuous. This says the inverse is also continuous. Okay, if t maps, t is an algebraic isomorphism and it is linear and bounded, then the t inverse, t is bounded. Okay, then t inverse is also bounded. That's what this is. Okay, which is crucial. So it doesn't follow automatically. It follows here. Because of, I mean, if the range is a closed subspace, range is a Banach space, then it follows. Okay. And this will be applied, this will be used to prove closed gap theorem. Okay.
Yeah. Yeah,
that's all. It says it's an open map. That means the inverse is, if the inverse exists, that is also continuous. See, this holds true, for example, a compact set. If you take a compact set, if there is a bijection, then the inverse is also continuous, because compact set takes, I mean, the map on a compact set take closed sets to closed sets. Okay. In particular, it will take open sets to open sets. So if you have a algebra, I mean, if you have an ordinary bijection, If you have a bijection which is continuous, then the inverse is also continuous. It's a homeomorphism for compaction. It's a map on a compact set is open map. It's a theorem similar to a linear map which whose range is closed is an open map, which is very, I mean, which is not immediate, but it follows from that category. Okay. So I will end the session. Thanks for your patience. Bye.
Sir, are we having any more classes in this course?
No, the class is over. We have only presentation.
Okay, so in particular on Thursday and Tuesday, we don't have any class.
No, we don't have any class. Okay. Whatever done in the presentation, I may comment few things. That's all.
That will be during the presentations only.
Correct. Yeah. That's all. But we have daily. Okay. We have next 3 days. We do have it. Okay.
Okay.
Okay then. Bye.
Sir, and the syllabus, so it is only from functional analysis and beyond, right? No, after Fubini and all that.
Correct. Correct.
Okay.
Okay. I don't know why it says. Anyway, goodbye. And take care.
Thank you.